Yeah.
And it was a way to simplify the surface, no,
Circle.
surface integral. No, no, a line integral over a closed surface.
Yes, line integral over closed surface, closed curve, not surface.
So,
So the
same
line
thing.
integral over closed
Manav is
curve.
there.
No, he's there, but I think his camera is off.
Yeah,
Anna,
I'm
are you
there. I'm
there?
there. Yeah,
Yeah,
one second. Yeah,
Yeah,
one second. Yeah, yeah, I'm
yeah,
there.
I'm saying
Yeah,
that.
well, just one. Yeah, yeah. Continue, sir. I'm
yeah.
listening. I'm writing also.
Okay.
Just one second.
Yeah. So the Green's theorem applied to the closed cyclic curve. That's called simple cyclic curve. Okay. And the vector field passing through that curve. So we find what is the work done from moving a particle from one place to another along that closed curve, right? So that work done can be found by using Green's theorem, isn't it? If you
Hmm.
notice that that closed curve or the anything like the region or whatever we learned so far is planar surface or planar curve. Like the curve was like this, isn't it? It was on one plane. It can be sit on a plane, right? That simple cyclic curve can be sit on a plane. But what if we have this type of curve, okay, which is or maybe this type of surface which cannot be sit on a plane, means which are not planar. Are you getting the idea here?
Hmm. Hmm.
What happen if suppose the vector field is passing through this type of surface or this type of curve, right? So what would be the work done? That we have
Hmm.
not done yet. Even while doing double integration, our reason was flat, right? Please verify. Our reason was flat, isn't it?
Flat.
That
Hmm.
was on xy plane. That is just a projection of level curve on xy plane, right? So our reason was flat. It
Hmm.
was planar. It can sit on a plane. But what happen if my curve or my surface is not planar? Then how do we find out the area or the work done if my curve is not planar and I want to move a particle from one point to another on this like 3D curve, you can say, okay? If suppose the vector field is passing through it, so that's completely different aspect of that, and that is dealt by Stokes theorem, right? So Stokes theorem is basically the generalized way of thinking about Green's theorem. Green's theorem was we had one restriction that that curve has to be on a plane, that I didn't mention while doing
Hmm.
Green's theorem because I don't want to complicate that your approach of thinking. Okay, so now we can move ahead with the concept where the curve is not planar. Are you getting the idea here?
Hmm.
Hmm.
Okay, so let's discuss the the first thing that's called surface integral, parametric surfaces, comma parametric surfaces, and then based on this concept, this basic idea, we can move ahead with the Stokes theorem and divergence theorem. Okay,
Hmm.
fine. So yeah, let me draw the surface here. Instead of region, we will call that as surface now. Okay, that surface like this. Okay, so this is a surface. The objective was to find out the area of this surface. Okay, So we can like have a, suppose this is a one patch on this surface, really small area, okay, and then we'll integrate over two dimension, like we'll apply double integration to find out the area of this surface. But since the double integration idea was that so far that worked on the planar region, right? Now our region is S, that's basically surface, right? So we must, like if you look at this patch on the surface, that's very small area. If you look at this from the top of it, okay, from the top of it like this, so this patch will be like, it will be seen as a region on xy plane for now, right? Like this, the projection of this patch will be on xy plane, that will give you the planar
Yeah.
region, right? That will give you the region. Now that can be dealt by double integration, right? Are you getting the idea here? The projection of this patch, see this is the surface, like this is the surface, the projection of that on xy plane, on coordinate axis plane, okay, that will be look like a region. Now got the idea here?
Hmm.
So like if suppose u and v are two parameters, hmm, u and v are two parameters, uh, like we want to convert this equation in parametric form. So let me just draw the thing properly. So this patch, okay, let's say the surface is Sij. This, the address of this patch is Sij. Okay, it will corresponds to Rij. Okay, on UV plane, because I'm taking the parametric equations here. So x, y, and z all are replaced by will be replaced in terms of u and v. Okay, so in new coordinate system, that is u and v will find a region, okay, and that region is Rij, that corresponds to Sij. Got the idea here? That's correspond to Sij, where u and v is basically the parametric form of the given equation. Okay, so I give you the combination of this idea here. Suppose this is the surface. Okay, suppose this is the surface. So the corresponding, let's say, we'll get parallelogram here, right? So this is the corresponding parallelogram we can find. So we can find the area of this parallelogram that corresponds to that small area Sij. Okay, this is Sij,
Hmm.
whereas it corresponds to region Rij. Yes, you've understood so far.
Yeah.
Okay, so now since we are finding out the area of Sij that corresponds to the area of region Rij. Okay, so in this diagram here, let's say the second diagram, this is the first one, this is third one. So in the second diagram, this difference is del u and this vertical difference is del v. Okay, and suppose this point corresponds to ui star vj star. Okay, that's the starting point. Just I'm taking any point you can take. These ideas we have already worked on, like for to understand the double integration or triple integration, because we apply summation over the small part of the region, right? And that gives the idea of integration. That summation converted into integration, right?
Is
So if,
the projection of Sij?
yeah, see, projection of
Oh, yeah,
Sij on UV plane, you can
yeah,
consider on UV
on
plane.
UV plane. Okay.
Okay, because I have converted x, y, z all in terms of u and v. Okay, in parametric
Hmm.
form.
Yeah,
So the area of Sij is same as area of Rij. So the area of
area. Yeah.
Rij is del u.
So what is diagram 3 showing?
3 is showing that the given surface can be considered as a parallelogram
Yeah,
with same area, because our region has to be on plane. So because to apply double integration, our region has to be on plane, right? Because we have only two direction for double
yeah,
integration, isn't it? We can handle only two variable if we have double integration, right? If you have a surface, it will have three variable involved. Now understand it properly. If we have three variable involved, that is x, y, z, I can convert all x, y, z in
yeah,
terms of u and v. Now these are the parameters, right? So we got only two variables now.
yeah,
X, Y, Z are converted into u and v. Okay, so we got two variable u and v. So we can like think of double integration if we have two variable. Okay, we can apply double
got it.
integration if we have two
Yeah,
variable. So we'll talk about with the example how we can convert the given surface in terms of parameter u and v. Okay, with the example, but for time being, you understand that if we have three variable, if we have a surface, right, x, y, z, that has to be converted into uv form. Uv form means the parametric
yeah,
form. Okay. Okay, so the area of this parallelogram will be del u ru star into del v rv star. Okay, this partial derivative is like giving you the direction along u axis and along v axis, and these are the magnitude of length. And suppose this is a parallelogram, I should have drawn the parallelogram properly. So parallelogram will have del u del v, and we know that it's related to, if you think about the sine rule, if you can recall sine rule, the area of parallelogram is a cross b, that is ab sine theta. Do you remember that stuff? I'm just trying to relate the
Hmm.
stuff that you have already studied long before here. Okay,
Hmm.
so del u ru star cross del v rv star is the area of the of the given patch. That's really small, area from the given surface. Okay, and that is equal to ru star cross rv star del u del v. Okay, ru rv are the vector, so we are finding out the cross product of that here. So an approximation to the area of S is, we'll apply summation because this is the small part of the given surface. So we'll apply summation here to cover up the entire small parallelogram, right? To cover up entire small parallelogram. Okay. So summation I goes from 1 to m, j goes from 1 to n, magnitude of this del u del v. You understood this so far here? This will give you the area of the small patch of the surface, right?
Hmm. Hmm.
So now this double summation can be replaced by integration ru cross rv du, and this difference is replaced by differential du dv over the domain of u and v. Okay, over the domain of u and v, because we'll set u is equal to something to something, right? V is equal to something, so that will be defined by the domain of u and v. Okay, so let's summarize this idea here as a definition. If smooth parametric surface S is given by the equation R u comma v x u comma v I cap plus y u comma v j cap plus z u comma v k cap. You understand this notation? The given surface is now converted into parametric equation. Okay,
Yeah.
we'll will like will hands on this like idea with the example where u comma v belongs to certain domain where the range of u and v are defined, that we can even find out with the given surface, like with the given uh, the boundary. And S is covered just once as u comma v ranges throughout the parameter domain D. Then the surface area of S is the surface area of the that that curve, not curved surface, is basically double integration ru cross rv dA that we just found here, where what is ru? R is the partial derivative of this vector form of the given surface, which is del x upon del u I cap plus del y upon del u j cap plus del z upon del u k, and rv is equal to del x upon del v I cap plus del y upon del v j cap plus del z upon del v k cap. Okay, got the idea here? This gives the surface area
Yeah.
uh, of curve surface area, I would I would say. See, if I say region, it means I'm talking about the flat region. If I say surface, it has to be curved surface area or any type of surface. Okay, so now let's start our topic, that is the surface integral. Uh, okay, don't give heading now. Okay, so okay, say this is just. Uh, can you recall this part? Double integration of f of x comma y dA is over a flat region R. Okay, what this gives us?
Mhm.
What this gives us?
This is
Volume,
Volume. If suppose f of x comma y is a mass density function, then
mass,
then the total mass
mass
of
of the
the
plate. Okay, mass of R,
plate,
thin plate,
yeah,
right?
disk. Yeah,
So,
yeah.
yeah.
and this gives the mass of R if f of x comma y is the mass density function of R. Okay, so what if R is not flat? Are you getting the idea here? Can we still find out the mass of the surface? Yes, obviously,
Yeah.
but we just want the mass density function, right? So you can keep writing, then the region is actually a surface S. A surface integration is basically this f of x comma y comma z, right? This is mass density function of
Mm.
surface. So I would integrate over surface, right? I would integrate over surface because that surface is not flat now. That surface is a that curved surface. So I would integrate over,
Mm.
like over S. Okay. So
Yeah.
you must notice that, like, I have replaced R by S and dA by ds. That dA was the area of the region. Here ds is the area of the surface.
So,
Yeah,
so wouldn't there be a triple integral because there are three variables
yeah,
f, x,
yeah, yeah,
y,
yeah,
and z
yeah.
there?
That what I'm explaining you. See, we have three
Okay.
variable x, y, z, but that I would convert
Hmm.
into parametric form u and v. So that is the like problem here, na? You notice the problem now.
Mm.
We got three variable because of the surface, that f of x comma y comma z is basically the mass density function of every point on the surface, right? That define every
Hmm.
mass density function at every point. That has to be f of
Hmm.
x comma y comma z, but it has three variable. So the problem is
Hmm.
we cannot handle three variable with double integration. So that
Mm.
so we need to convert that xyz in parametric form, such as u comma v. Okay, and then we can easily define, like, we can
Hmm.
easily apply double integration over that region. We'll convert
Hmm.
s into r. See, when we convert s into r, we'll get u and v. Can you see that? That sij is
Hmm.
being is corresponds to rij. Okay, so that's the whole idea here.
Mm.
Okay, so this is surface area. Okay, you can write this is mass density function. The projection of S, the projection of our surface S onto a coordinate plane give us R. Okay. Now write three, like, based on the z simple, y simple. See how we handle triple integration. We had three simple, right? We had R3 simple, that was z simple,
Yes.
y simple,
Hmm.
x simple. We take any simple, like maybe z simple, and then we find the projection of that on xy plane, and then like we apply the triple integration, right? That was the idea. Similarly, we can have like this for double integration. In this case, if I want to convert this s, this surface, if I want to convert this s into UV plane, okay, that will give us the region R now. So double integration over R, f of x comma y, g of x comma y. Hmm? Are you getting here? See, I'm taking z simple.
Hmm.
Hmm? I'm taking z simple. So z is equal to g of x comma y, right? Z is equal to g of x comma y. So I'm
Yes.
converting g into x and y form. So what is this like? If I we had f of x comma y comma z, that was the mass density function, right? So this will also give you the mass density function over region R for every point. But this won't give you the, see, this is the mass density function. We are converting ds to, ds to dA. We are converting ds to dA, right? So there has to be some, you can think of Jacobian. See, we are dealing with lot of things together here. You can think of like ds is being
Hmm.
converted into dA. So like a Jacobian or r dr d theta, we have something here that is gx square partial derivative. These are the partial derivative. Okay. For time being, you just consider this. Shortly, I'm explaining that because we already found this. You can even relate here itself. What is this basically? See, the S is being converted into, you know, dA here. ds is being converted into dA, right? So what is Ru
Yeah.
cross Rv? That's the vector product, right? And if you apply the vector
Hmm.
product, we'll find, see, magnitude of vector product. Are you getting that? That's the double line, oh, uh,
Hmm.
around that vector product. It gives the magnitude, right? So the magnitude is
Hmm.
basically here. This is the magnitude. That was Rv cross product Rv. That will give you, magnitude. You can think of that. That will give you the magnitude. I'll just explain you this with example. Are you getting the idea here?
Hmm.
Okay. So just write down all these three different simple. The first one was z simple. So f of x comma y comma z ds is
So you're
equal to,
saying the
yeah,
so you're saying the square root gx square plus gy square plus 1 is the Jacobian. That is the
yes,
Jacobian, right?
yes, Jacobian, or that
Hmm.
can be found like the magnitude of this. That is same as the magnitude. So this is the area. Are you
Hmm.
getting that? This is the area of the surface. and I'm just replacing this
Hmm.
part. If you have this mass density function as 1, what it will give you, like
Hmm.
if you put mass density function as 1 in double integration, what exactly it give us
Yeah.
then? It will give us the area of the region,
Area.
right?
Hmm.
So if mass density function is 1, so this the remaining part will give us the area, right? Right.
Right.
So dA, this something dA, here something dA. So you can relate that this vector product is same as the magnitude of that vector product is same as this part. Are you getting the idea here?
Hmm.
And that is what the magnitude is. Magnitude of vector is basically square root of. Are you getting that? Square root of partial derivative square, sum of the partial
Yeah. Yeah.
derivative square. Okay. So we'll deal with some
Hmm.
example here now after this. So it was for Z simple. Now complete the idea here for the other two thing. So f of x comma g of x comma z. Okay. So this is y simple now. Gx square g square plus 1 dA for surface y is equal to g x comma z. F of x comma y comma z ds is equal to r f of g of y comma z comma y comma z for surface g x is equal to g of y comma z. So see, these are the projection. If you look at the projection of the surface from along, top of the z axis, that projection will be on xy plane. If you look at the surface from top of x axis, okay, or right extreme right of the x axis, that you will see the projection of that on yz plane. Are you getting the idea? If you look at the surface along y-axis, you will look at the projection of that surface on xz plane. So based on these three idea, we had R3 simple, isn't it? So similarly,
Hmm.
we are just taking here that idea to find out the area of the surface.
Yeah.
Now write down one example here. So S x plus 2y plus z ds. Okay, and S is defined as y plus z is equal to 4 inside x square plus y square is equal to 1. Okay, so can you imagine our surface here?
Yeah.
Where is our surface? What is x square plus y square is equal to 1?
It's a circle.
Circle.
It's Y. Z simple.
Yeah.
uh, it's a circle or cylinder. See, it is independent on z, right?
Yeah. Z simple it's a circle, right? In Z
Yeah,
simple it's a
yeah.
circle.
So x square plus y square is cylinder, and y plus z is equal to 4 is some plane. Okay,
Yeah.
is some plane that intersect the cylinder, right? So that would be the surface. Our surface would be like this. Can you see that? Our surface would be like this. Okay, because it intersect the
Would be
cylinder.
like that, right? Yes.
Yeah, yeah, ellipse kind.
Yeah.
Okay.
Yeah.
So which simple we'll go for z
Hmm.
simple, right? Because that's easy. If you take go for x simple or y simple, you will have to take the square root. Okay, and that's not recommended, right? So we'll go for z simple. So z is equal to
Hmm.
4 minus y. Okay, and based on the above formula, we'll find out gx and gy. Okay, see, so this is like g of, so what would be like gx here? That's the partial derivative of z
Hmm.
with respect to x.
Will be zero,
0.
Yeah.
right?
Yeah, and partial derivative of g with respect to y,
Minus
Minus
one.
one.
minus 1. Okay, so the surface area, okay, so we can like convert this in terms of x and y now. So x plus 2y plus, what is g? Z is 4 minus y. Z is 4 minus y, right? And how do we replace ds?
Hmm.
ds is replaced by square root of
Root
g of x
of
square plus g
one
of,
zero
so
square
0 is square minus 1 is square plus 1
plus
dA.
one root two. Yeah.
Hmm.
Hmm.
So we can further simplify this. Now this is on region R. So we can further simplify x plus y plus 4 root 2 dA. Okay,
Hmm.
over region. So what is our region now? The region is that corresponds to the given surface. Our R is like that corresponds to S, right? So y plus z is equal to 4, x square
Hmm.
plus y square is equal to 1. So our region will be on xy plane, isn't it?
Hmm.
Xy plane. So x square plus y square is equal to 1. That's the unit circle.
Hmm.
Okay.
Yeah.
And x square plus y square is equal to 1. And y plus z is equal to 4. We are on xy plane. So we'll put z is equal to 0. That
Hmm.
gives y is equal to 4. So where is y is equal to 4? Somewhere here. Okay. So it is not basically line. It's
Hmm.
line on xy plane, but it's like plane. Are you getting that? Y plus z is equal to 4.
Hmm.
That's the plane that will
Hmm.
intersect. It is not intersecting on xy plane, but that will definitely intersect on space. Okay, above xy plane,
Hmm.
right? You can think like this. Suppose this is the cylinder. The plane will
Yeah.
intersect.
The intercepts are y is equal to 4 and z is equal to 4, right?
Yeah,
For that plane.
yeah. It may be oblique. Doesn't matter, right? So that's the
Hmm.
concept here. Okay, so can you solve this now? Can we set up the double integration?
Yeah, I converted it into polar form.
Polar form. So x is equal to r cos theta, y is equal to r
But
sin theta.
uh,
R goes from 0 to 1 and theta goes from
Hmm.
0 to 2 pi.
Hmm.
R cos theta plus r sin theta plus 4 root 2, and dA is r dr d theta.
Hmm.
So we can simplify this and our answer would be 4 root
Hmm.
2 pi. What is this? What is 4 root 2 pi?
area under the surface.
If xy
This.
if this function is mass density function x plus
I
2y
was gonna
plus z.
ask, how do you know?
Yeah, if I'm saying
Then it
that.
is
I was gonna,
mass.
No, no, I'm just saying that if it is the mass density function,
hmm,
then it would be the
Mass.
mass
Total
of
yeah,
mass.
that surface.
Yeah.
yeah. Hmm.
Mass if f of x comma y comma z is equal to x plus 2y plus z is mass density function. Okay, did you
Hmm.
understand so far?
Hmm.
Okay, now give the heading parametric surface. So for f of x comma y comma z and x is equal to x u comma v, y is equal to y u comma v, and z is equal to z u comma v. Okay, so all x y z are is written in terms of u and v. So the position vector of every point on the surface can be written as, you understand the thing like position vector. If I'm saying, if I write r bar u comma v, do you understand that what is position vector? Okay, fine. So position vector is like
Hmm.
define every point by using vector. Okay, the reference is
Yeah,
taken
yeah.
from origin.
Right.
Okay, so that's why the vector is very easy to interpret the surface.
Hmm.
So r bar u comma v is equal to x I cap plus y j cap plus z k cap. So what would be f of x y z? That is r bar u comma v is equal to x in terms of parameter now, y u comma v j z u comma v k. Okay, now take example like how to convert the given surface in terms of parameter. If suppose I give you a surface which is x is equal to root y square plus z square, what is this? What this equation denote? Is it cylinder, circle, plane, cone? What? What is this?
It's what will it called? Hyperboloid. No, 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 no.
You can put different values for x, no? And you can have idea about the surface. If you put x is equal to 0, right? So what would be y square plus z square is equal to 0? That's the point. If you put x is equal to 4, what would be y square plus z square?
Hmm.
If suppose x is equal to 2, not 4. If x is equal to 2, what would be y square plus z square? So y square plus z square is equal to 4, right? So that's a circle.
Hmm. Hmm.
Hmm?
Hmm.
A disk, right?
No, no. Suppose this is x-axis. If you put x is equal to 0, so that's the point. Okay.
Hmm.
Now if you put x is equal to 2, so that's the circle like this. If you, so you're not getting this.
Oh, it's a yeah, it's a cone. It's a
Cone.
cone,
Yeah,
which is
it's a cone.
yeah. Hmm.
Huh?
Hmm.
We just saw in, I think, had I given you the example? No. So this is a cone, right? So
Hmm.
x is equal to root y square plus z square represent a cone. You don't know the height of that cone. Okay. So the question is, how do we convert this in terms of parameter? Okay. So if for a function like that already solved for a variable, let okay, that already solved for variable. See, this x is already solved in terms of two other variable. So we'll take the other variable as u and b. So that's how we can convert the the given rectangular coordinate, not rectangular, maybe in the xyz coordinate system equations to parametric equation. Okay. So if suppose we set y is equal to u and z is equal to v. Okay. So what would be x? X is equal to square root of u square plus v square, isn't it? So that's how we can convert the given surface into parametric form. Did you get the idea here?
Hmm.
Okay.
Yeah.
So you can mention, this is trivial, like this, very simple. Okay. So you can write for
Yeah.
function already solved for a variable, let other variable be parameter. Okay. Let other variable be parameter. Then how do we write the r bar uv, the vector form of the surface? We got x, y, and z component here, right? We
Hmm.
got x, y, z component here. We can simply plug them in this equation to find out the vector form of the surface. So since r
Hmm.
u comma y is x I cap plus y j cap plus z k cap, so r bar u comma v is equal to root u square plus v square I cap. Okay, we are working the same example. Plus u j cap plus v k cap. Understood?
Hmm.
Okay. So this is called the parametric surface. What was the heading? Parametric surfaces. Okay.
Hmm.
Okay. Next example. Suppose I give you x square plus y square is equal to z square. What is this?
This is also a cone, right?
Yes, this is also a cone, but what is the difference then from the previous cone?
It's it's the axis is different, which it's like
Axis is
around
different.
the cone.
Yeah, the axis is along z axis. And what else?
Yeah.
Can we go below xy axis, below xy plane, or can we go along negative z
No,
axis?
it's only
Yeah.
No.
on the positive.
Hmm.
Wait, we can. The z is always
Z.
positive.
Yeah. So suppose this is z axis. This is 0.
Hmm.
So along positive z direction, this is the cone. Along negative z direction, this will be the cone. So we have set of cone here, right?
Hmm.
Are you getting the idea here? So how do we convert this in the parametric form? See, this corresponds to circle, right? If
Um,
x square plus y square is
Yeah,
equal to
r
r,
cos t sin cos.
yeah. If z is equal to r, or if you set z square is equal to r square, that gives z is equal to r.
Yeah.
So x square plus y square is equal to r square, that corresponds to circle. So we know one thing
Hmm.
for circle, that x is equal to r cos theta and y is equal to r sin theta. Okay,
Yeah.
and z is equal to r, right? Z is equal to r. So the parametric form
Hmm.
of this cone, pair of cone, will be r u y u comma v, because if you write, see, the parameters are r and theta here, right? Parameters are r and theta. So if you write r here like r bar, there is no issue, but and there is no confusion also. But for the sake of like different
Hmm.
notation, I would use uv rather r theta. Okay, so u comma v is equal to xi cap plus yj cap plus zk cap. Okay, and correspondingly we can change this to like r cos u, no, u cos v, right? R is u, theta is v, so u cos v, u sin v, right? Any confusion? Any confusion here? See, instead of taking r theta, I am taking uv. That's it.
Hmm.
So x is equal to r cos theta I cap plus r sin theta j cap plus r k cap. Sorry. So mm, I'm replacing variable, but I'm not replacing here. So u cos v, u sin v, and u. Okay. So see, I'm relating here the vector product with the formula that I had given you here. Okay. Now I'm going to relate this term with the vector product. Okay, this one. So write down like for the special case of a surface S with equation c is equal to f of x comma y, where x comma y lies in t and f as continuous partial derivative, we take x and y as parameters. The parameter equation are parametric equation are, see, I'm taking x and y as parameters, so x is equal to x, y is equal to y, z is equal to f of x comma y, right? So far we have dealt with this, right? Instead of x and y we can take u and v also, no issue with that. So what would be like, let's take u and 2v, u and v only. You may be confused because of many notations, u and v. So u v, u comma v. So what would be RU? RU, partial derivative of,
Um,
you know, x with respect to u, I cap.
Yeah, dx
is
del x by del u.
Yeah. So that would be just one I cap,
one. Yeah.
partial derivative of y with respect to u, that's 0 j cap, plus partial derivative of f with respect to x or u, not x, u, with respect to u k cap. Okay. What would be RV?
Hmm.
What would be RV?
RV
Yes.
would be 0 I cap
Yeah.
plus 1 J cap
Yeah.
plus del F K cap.
Very good. So now we'll find out cross product RU and RV. So I J K10 del F upon del U 01 minus, sorry, del F upon del V, not minus. Will you able to find out this?
Yeah.
Let me know the answer.
Yeah, I got the answer.
Let me know the answer.
It's the minus del F del U I
I,
cap
yeah,
minus del F del V
del
G cap plus K cap.
j cap
Perfect.
plus, yeah.
So what would be the magnitude of this?
Mm,
Oh yeah, yeah, yeah. You get the this
yeah,
thing.
del f by del u squared plus del f plus 1. Yeah, u squared plus 1.
Do you notice
You
this?
get the
I
formula.
verify the previous
Yeah,
assumption.
Yeah,
yeah.
yeah.
Hence, hence, you guys have a lot of patience. See, when I was a student, I wouldn't have not allowed teacher to move ahead. So hence, surface area AS D. So del F upon del U whole square, del F upon del V the whole square plus 1 D. Okay. Now write down one problem. I hope you got everything so far. Okay.
Yeah.
So write down a question. Find surface area of x square plus y square is equal to z square. The This is same as the example we worked on. I think so. This is R you can consider, right? Directly. right?
Sir, 2 minutes. I'll be back. I need to go to the bathroom.
Okay. So R like the vector rotation of the surface is u cos v I cap plus u sin v j cap. This is the parametric equation of the given surface. Now find out the surface area. I am taking this from the see. This is the same as the previous example. Is there any
Hmm.
confusion here? See,
Hmm.
we got this and the
Hmm.
parametric equation is this. Right? I just copied it.
Hmm.
Now find out the surface area. What will you do first?
You find the Jacobian thing.
Partial derivative. Partial derivative with respect to u, right?
Yeah,
And
yeah,
partial
yeah,
derivative with respect
yeah.
to v.
Hmm.
So what is partial derivative of r with respect to u? That's cos
Uh,
v I cap
V I cap plus sin V J cap plus K cap.
plus k cap. And what is partial derivative with respect to v?
It is minus U sin V cap, sin V I cap
J cap.
plus U. Why J cap?
I
U,
cap, no?
yeah, yeah, I cap, sorry. Yeah, I cap.
Uh, yeah, U cos V J cap
U cos v j cap
plus zero
plus 0 k cap.
plus zero.
There's some correction here. I cap, j cap. Okay, so
Uh,
Ru cross Rv. We'll find out the cross product, right?
hmm,
I
hmm.
j k. Find out this cos v sin v 1 minus u sin v u cos v 0.
Yeah, so when you simplify, you get minus U cos V I cap
Minus
minus
u
U sin
cos v I cap minus u sin v j cap
minus
plus
sin V J cap plus U K cap.
u
U
k
K
cap.
cap.
Perfect. So now we'll find out the magnitude of this, right?
Yeah.
So that will be u square cos square v plus u square sin square
U
v
square,
plus u
U
square
square plus U square plus 1. U square plus U, 2U square.
2u square, which is root
Root of
2u.
U square.
So the
Which is,
area will be,
Yeah.
yeah.
now the surface area is, the surface area is equal to this RU cross RB dA. Okay, so surface area is equal to root 2U dA, isn't it?
Hmm.
So what was like what was U and V? There are two parameter U and V. What was U and V in this case for this example?
So was the R, U was the R and V was the theta, right?
Yes, U was the R and V was the theta. Okay, so
Yeah.
R is equal to V, theta is equal to R is equal to U, theta is equal to V. So we can set up double integration here. We always take like dA is being converted into polar form. So instead of writing R dr d theta, right? What should I write?
Hmm. Right, U du dv,
Are you sure?
right? You're saying instead of R dr d theta,
Hmm.
in this case, we, right?
We already found Jacobian here.
Oh,
That's
Yeah.
root 2u. We already found Jacobian. So dA is directly du dv.
Hmm.
Root 2u. U goes from 0 to, that's not defined here. So let's generalize this. U goes from 0 to r and V goes from 0 to 2 pi. That's complete revolution. Okay, if you look at the example here, okay, this r is not defined. First of all, this r is not defined how long this is going, and theta is obviously 0 to 2 pi. Okay, theta is 0 to 2 pi. That's a complete rotation. Okay, we already found the
so
Jacobian.
R is a
That's
variable, right?
r is variable. We are generalizing, like we are finding out the general formula here to find out the surface area that dependent on
Hmm.
r. Okay, so that will be 0 to 2 pi root 2 by 2 u square. U is equal to 0 to u is equal to r dv root 2 by 2, isn't it? 0 to 2 pi r square dv. So root 2 by 2 r square is like constant. We are integrating with respect to v. So v 0 to 2 pi root 2 pi
Wait.
r square.
Just
So
put.
this is the surface area of x square plus y square is equal to z square. Okay, let's find out, or let's verify this basically. See, our cone is like this. Okay,
Hmm.
along c, this is 0. So our cone is like this, right? So if I take this as
Yeah.
this, z is basically h and this is r. Can you see the diagram properly? If height is basically h, right, z is equal to h. I'm taking height as h and radius is r. So how do we find out the surface area of a cone? What is the surface area of cone?
1/3 pi r square.
Pi r. Pi r square.
Surface area of a cone, pi r l.
Oh, surface area. Sorry,
So you mix
that is pi r l,
L
which
is
is
the
where
slant edge.
pi r square plus pi r l.
Yeah,
There
yeah,
is no lid. There is no lid. I understand you, Mano. But there is no lid.
Okay. If
Okay.
there's lid, yeah, yeah, yeah.
So pi r, the square root of r square plus h square. Okay. So the surface area is equal to pi r square root of r square plus h square. And what is h here? H is r. Okay. Here we took h is equal to, see that this is radius. Don't confuse. This is radius, right? This is radius.
Mm.
And this h is r. That's how, are you getting that?
So we get 2 pi
0
r
to
square.
u goes
Yeah,
from 0 to r, no? So that
yeah,
z is h, h is r, likewise.
yeah.
So pi r root 2 r square. So pi r root 2 r, which is pi root 2 pi r square, which is same as this, right? So this verify the surface area of a cone here.
hmm.
Any doubt? Any doubts so far?
No.
Okay. So let's do last example on this. X minus y upon root 2z plus 1 ds as defined as r u comma v is equal to u plus v I cap plus u minus v j cap plus u square plus v square k cap, and u goes from 0 to 1, v goes from 0 to 2. Set up, find out the, yeah, set up the double integration first of all. Suppose this is the mass density function. Okay, we are finding out the mass. Then if suppose that function is mass density function, then the result would be the mass of that plate, mass of that surface, isn't it?
Hmm. Hmm.
So find out the mass here. So what is the formula? Let me revise the formula again. See the surface area. So far we have done the surface area. Surface area is double integration over d ru rv dA. Okay. Now for parametric surface, so the mass, if suppose the function represent the mass density function, then this will be r comma u and the vector product, its magnitude dA. Got the point here? This will give you the mass because this function is mass density function, isn't it?
Hmm.
Okay, now apply this formula and find out the mass. So for that you'll have to find out partial derivative with respect to u and partial derivative with respect to v. Let me know the values of it. Any doubt, Mano?
Mm.
So R use I cap plus J cap plus 2 U K cap.
Okay.
and V is I cap plus J cap plus 2V
I
cap.
cap minus j cap plus 2vk cap.
Minus J cap, right? Yeah.
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 Sorry, I cap minus J.
So now we'll find out the cross product. I cap, j cap, k cap, 1 to u, 1 minus 1 to v. So 2v plus 2u I cap minus 2v minus 2u j cap plus minus 1 k cap, and that corresponds to 2v plus 2u I cap plus 2u minus 2v j cap minus 2k cap. What is
Yeah.
x? What is x, y, and z? X is equal to u minus u plus v, y is equal to u minus v, and z is equal to u square plus v square, right?
Hmm.
So double integration. So what is x? X is u plus v minus u minus v upon root 2 u square plus v square plus 1, isn't it? And ds is replaced by mod of,
Hmm.
mod of cross product. So that would be like square root of 2v plus 2u square plus 2u minus 2v square plus minus 2 the whole square. Okay, dA, isn't it? And u goes from
Hmm.
Yeah.
0 to 1, v goes
0.
from 0 to 2, right? You can change dA to
Mm.
du dv. This should match with the variable here, right? Are we going to solve this integration?
Hmm.
Not really. We just wanted to set up this.
Yeah. It's very complex.
Maybe if you can like 2v upon this, we can solve this maybe, but we'll not try.
Hmm. Hmm.
Okay, so we stop here for today because next is a
Hmm.
completely different topic. Different means in concentration we'll talk about the surface flux and other stuff, and then we'll move to the stocks theorem. Okay.
So I don't know if I'll be able to make it now because my college is starting
Yeah.
now. So I
So
mean, I can watch the recordings or whatever.
yeah.